Okay, so I will record this lecture just in case not everyone is here. But like I said, we're gonna continue talking about atoms and the periodic table. But first, okay, and so this chapter, we started last Monday. We covered the atomic theory, the structure of atoms, elements, atomic number, isotopes, and the atomic weight. And today we're going to go in more detail into the periodic table, the different characteristics, the structures of atoms, and electron configurations. And these electron configurations, it might seem complicated, and it is complex, but once you understand the configuration, it helps you understand the properties of elements. And once you understand the properties of elements, it helps you understand their electron configuration. So we're going to go over all this, and I wish you could know everything all at once. We have to kind of go in order, and so sometimes like you might be a little bit confused, but if you'll wait like 5 minutes, things will become clear. Okay, is this really where? Okay, I wanted to start further down. Fun times. Okay, this is where I wanted to start. Okay, so we're continuing with this, the atoms in the periodic table. But first, thank you to everyone who submitted the quiz. If you submitted it like before 10 or 11, I got it graded. If you submitted it like at midnight on the dot or after, I haven't graded it yet. But one of the things you'll notice, like there are like free points in there. So if you don't submit, then you don't get any free points. But if you do submit, then you get free points for telling me things that have slightly nothing to do with chemistry. But there was one question about music. So I'm making this playlist of all the music that y'all had requested, and I'm just going to push play on this Chemistry 100 playlist at the beginning of class. And so we'll get a little bit of everybody's diversity. So today was Bob Marley. Thank you, whoever submitted Bob Marley. Tomorrow it'll be a little bit different, and we've got like until January, 3 days a week to get through all of our favorite music. So maybe you'll learn something new about, maybe you'll learn to find some new music. Maybe you'll hear some music that you like. Maybe you'll be exposed to new music that you never heard before. But it should be fun. So it's not just me playing my favorite bands, it's me playing your favorite bands. Cool? Okay, and then there's a link if you want to check it out and listen on your own. I haven't gotten, like I said, I haven't gotten everyone's songs in there, but with like 6 people's songs, it's already like an hour long. It'll be fun. Okay, the other cool thing about quizzes is it's a chance for you to sort of anonymously ask questions. I don't, like, when I'm grading, I don't look at the name of what I'm grading. I just grade the content. And then I'm able to like pull questions and then discuss them as a group, and nobody knows that you're the one that asked the question. So by putting questions in the quiz, it's a way for you to ask questions and get responses, and everybody else can hear the response, and then nobody knows that it was you who asked it. So here's some of the questions from the quiz. Okay, there were a decent amount of math questions. So do we always have to use significant digits? I'm going to say usually yes. So you should always round to an appropriate number of significant digits. If there were only 2 significant digits in the question and you give me a number with 8, that's like way too many. So try to round appropriately. Do we always have to use scientific notation? No, only if the question asks or if you feel like it. You can write 200 if you want to write 200, or 2.0 times 10 to the appropriate number. So that's your choice. But if it says it, you should follow the instructions. So still have questions about dimensional analysis. It's vague enough that I don't know exactly how to answer it. But I would keep practicing. If there's a specific problem that you're struggling with, Tuesdays are the day to really get feedback on that. Kyle can like walk around the room and you can raise your hand and you can work on a specific question. And then also on Friday, I'll Friday, we're gonna do some homework in class, and I'll also go around with each one of you, and if you have a specific question about a specific thing, that's the time to get that asked. But Kyle did some really beautiful problem solving up here. Do I have a conversion sheet? Your conversion sheet has these equations, and you can move variables around. So I just have to get comfortable. There's one right there. Thank you. That one, yeah. And so there was one about like, let's see, one. So like this was one that we were working with. So if you're given this equation, density equals mass divided by a volume, you can rearrange every single equation. So you can also say density times volume equals mass. And so depending on what you're given, we move things around. So if you divide m by v, you can multiply the d by the n. So multiply this cancels out. We get d times d again. So every single one of these equations, you can rearrange it to solve whatever you're solving, to solve the appropriate the question at hand. So y equals mx plus b. If you want to solve for x instead of y, you subtract b from both sides. Y minus b equals mx. Divide both sides by m. X equals y minus b divided by m. So every single one of these equations that you've been given, you can rearrange it to solve for the variable that you're missing. So you'll be given like 3 of the 4 variables, and you solve for one, and it just requires this moving around. So multiplication and division go together, so adding and subtracting go together. And we'll work on a couple more equations. But this is one, if you like math, there's like known answers and things that are like easily divided by, there's like a logic. Biology is a little bit more uncertain and like, but yeah, if this is the math part of chemistry, you either love it or you hate it, but with practice, you should become comfortable with it. Any particular questions about some formulas that y'all been working with? How many labs are we gonna do? 15. I passed out a syllabus, assuming anything goes wrong. There's more or less 1 lab every single week, with the exception of before some exams. There's like a practice exam day. So there will be like 2 weeks of lab where you don't have a lab, you just practice. And there are 2 exams. There's one on November 22nd, which is like the Friday before Thanksgiving. So if you know you're gonna miss the Friday before like the Friday before the week off of Thanksgiving. So if you know you're gonna miss that day, like let us know so we can work out a makeup. And then there's one on the end of the semester, January 25th. Midterm and a final, yeah. 1 midterm, 1 final. That's pretty standard. The other sort of standard is 2 midterms and a final. Because a lot of times the course can like really easily be divided into 3 parts. So sometimes you have 3 exams, usually just 2, and it depends on the professor. Okay, this was like a really great question because we didn't cover it in lecture, but I think it did come up in the lab. So specific heat question. Is there a difference between the heat energy equation and the heat condensation equation? Yes. So the specific heat capacity is our constant C in this equation. Energy equals mass times the change, but times the specific heat capacity times the change in temperature. And so this heat capacity refers to ice, water, and gas. And so when you have a liquid and you heat it up a couple of degrees, but it stays a liquid, there's a specific heat energy for that. When you have a solid and you heat it up or cool it down, but it stays a solid, there's a specific heat capacity for that. And so this, like, you add energy and you heat up a solid or a liquid or a gas. That's this temperature on the left. However, when you get to the temperature where something changes states, where it goes from a solid to a liquid or a liquid to a gas, you add a ton of energy and the temperature doesn't change, but it does change states eventually. And so this here would be like the heat of freeze, the heat of melting, or the heat of freezing. And this would be the heat of vaporization or condensation. So in these equations, Q energy is equal to mass times L is that heat capacity for changing states. There's no change in temperature in this equation because you aren't changing the temperature. You're staying 0, there's ice at 0 degrees and there's water at 0 degrees. And it takes energy to convert between the two. And that's this heat of vaporization. So if you asked how much heat would it take to take a solid to a gas, it's like 1, 2, 3, 4, 5 different equations. Because there's 5 different constants for the heat capacity. Does that make sense? Awesome. So that would be like a very hard problem. Like math, that would be a very complex problem mathematically, asking like how much heat would it take to take negative 10 degree ice and turn it 120 degrees Celsius gas. Because you have to convert the energy required to change the temperature, then convert, change phase, and change the temperature, then change phase, and change the temperature. And I don't know that I have seen problems like that floating around, but that one's a little complex.
That'd be like a problem we do right now.
I've seen it, and it is in the like word bank of questions that I could choose from, but I chose not to do one like that. It's like a little bit unnecessarily complex. If I did give one, I'd find a way to make it really easy and like take out some steps. Yeah. But just like this is, because I have seen it kind of like floating around out there, like it is a word problem. You might encounter it in the future, like in another class. Just wanted to at least introduce you to the fact that these things exist. And like this is this figure was in your book and we kind of went over it, but yeah, you can have ice at 0 degrees and water at 0 degrees. And when you try to change their state, you're adding a bunch of energy. The temperature doesn't change, but you do need energy to change states. Okay, so this was a fun one. Okay, so I think y'all got this question, and that's why it came up. Would my drink heat or cool if water vapor condenses on it? So here, when condensation releases energy into the environment, so when the water vapor condenses on your cup, it's going to release a tiny amount of energy. Your drink could heat up, but it's like negligible. But this condensation releases energy into the atmosphere. So like when you I think one reason why this is really confusing is because if you think about when you sweat, like when you sweat, you're like releasing energy in the form of water on your face. So it is a way to cool off. So sometimes it's kind of thinking about like where the release is coming from. But water vapor, the environment is releasing the energy and it's sending that energy to your cup of coffee. Any questions about either of those? Okay, rockets. How do chemists make cool stuff for rockets? We will talk about that more in future chapters. I know you want to learn today, but we kind of cover the basics before we can get to the cool stuff. But there's molecules when you put them, so some molecules, when you put them in close proximity to the others, they release energy. And so we'll get to that later. But so stay tuned for rockets. Okay. Same thing for nuclear fission. Want to know how nuclear fission comes into play with energy? This is chapter 12. This is the very last thing we'll get to, so not today. Okay. There were like, I think at least 2 questions that are kind of related to what we're doing today. So I thought I'd go over it. This image is it's in Canvas. So I put a link to it on the modules page. It's called like Atomic Theories. So the very first atomic theory was probably spoken about by people who spoke in Greek languages or like not in English. And so he had a very vague, Dalton was the very first one who proposed an atom. He had a very vague understanding of it. He thought there's a Greek word called atomos that means individual. And he thought that there was an atom was the smallest individual particle. 100 years later, the guy was like, no, it's not just, that's not the smallest thing. There are positive and negative charges floating around. He didn't know how they were floating around. 5 years later, somebody was like, no, they have orbits and they're floating around in specific things, kind of like astronomers think of planets. And there was a nucleus with charge at the center. And so he got that right. There is a charge at the center. There are electrons floating around in space. This guy Bohr, which we're going to use, this is a Bohr model of the atom. And it has atoms in concentric rings that have different energy levels. We're going to learn how to draw. So he was right and he was wrong, but the way that he drew molecules is still useful today and it's still used a lot today. And so we're going to go over that. So first they talked about it, then they started drawing it to illustrate it. They're so tiny we can't see it. And then the last model, that's the one we still use today, is it's like, well, they're not really floating around in specific orbits. They're kind of anywhere at all times, forming an electron cloud. And that's the model that's accepted. But this planetary model and the nuclear model, we still base a lot of our understanding on those. So 200 years later, a lot of these concepts in the atomic theory still hold true today. Okay. The way we know, okay, oh, here's one video. Like if you Google mass spectroscopy, they played a lot with helium. Helium is that top right molecule, helium. Basically, they like bombard it with electrons and it doesn't accept any electrons. It just gets really excited and it makes this beautiful color. And so sometimes when you heat elements up, they emit colors. And that's what you're going to do on Wednesday. Okay. And so basically, one thing that they noticed there, so this mass spectroscopy, what it does is it analyzes the mass to charge ratio. So you're able to go like, okay, this thing weighs this much, and this is its charge. And you can go like, oh, this helium weighs a little more than this helium. Why is that? And so this mass spectroscopy of neon, is how they were able to discover these things called isotopes. So neon, everybody see neon over here? Where is neon? So neon 10. Neon, if its atomic number is 10, how many protons does it have? 10. Exactly. And its atomic mass is 20.180. And the way that it's 20.180 is it means that some molecules of helium have more than 10 neutrons. So helium, neon 20 has 10 neutrons and 10 protons. And this is how much it weighs, 19.999. Neon 21 has 10 protons and 11 neutrons. It weighs 20.99. It's rarely found in the Earth. Neon 22 is like an 8% abundance in the Earth. It has 12 neutrons and a mass of 21.99. And so neon 20 is the most common. So it's most common to have neon with 10 protons and 10 neutrons. Really rare to have 11 neutrons. Fairly common to have 12 neutrons. And so the way we get the mass is we add up the relative abundances of each of those. So we take the first abundance, 90.92%, times its mass, plus the second abundance times its mass, plus the third isotope's abundance times its mass, and you get 20.17. So I do think there is a problem like this. Maybe not. But this is how they come up with that number. This is why that number is not a round number for the atomic mass. Even though we talked about last week, the mass is the number of protons plus the number of neutrons, because there are different abundances of each of those, we get decimals with our atomic masses. Okay, one more question was, how does varying the particle change the electrons and neutrons? And I found like a blog that's pretty good about this. How does changing number of subatomic particles affect it? So is this big enough? It says this in your textbook, but not as many words. And then I'm going to go ahead and we're just going to go ahead and pass out this is our new homework. Okay, I should probably. So this first one, can anybody read the bottom line? If the proton number changes, what happens if we change the number of protons?
Protons are gained or lost when atoms are used with other atoms. Proton numbers characteristics that remains each other.
Yes. So the number of protons is characteristic of an element. So if you change the number of protons, you change what element you're looking at. Okay, so that's part of this table here. It says it in so many more words in your textbook. Oh, great. Okay, and we'll scroll down. If we change the number of neutrons, can anybody read what happens if we change the number of neutrons?
When neutrons are gained or lost, an isotope is formatted by something called an element heavy.
Yeah, yes. Oh, I skipped you. Sorry, did I skip anybody else? Oh my goodness. Okay, so when you add neutrons, you change the mass. Because the mass is protons plus neutrons, but it's still the same element. It's just heavier or lighter. So this would be beryllium-4. Beryllium-4 has 4 neutrons. Beryllium-5 has 5 neutrons. So their mass, this mass would be 4 plus 4 equals 8. This one's mass would be 4 plus 5 equals 9. So this one's heavier than this one. And then lastly, look, we have a Bohr model here. We're going to draw these later. Anybody can read this last one?
Electrons are gained or lost in ions form. If electrons are gained in ions form, electrons are lost in ion.
Yes, okay. So ions are charged particles. So this lithium, it has 1, 2, 3, 4 protons in the center and 1, 2, 3 electrons in the outer orbit. If it loses an electron, it's going to gain 1 more charge. I feel like it might have 1 too many. I think they drew this wrong. It's supposed to only have 3 protons in the center. But that's okay. People are human. They make errors. So anion means it has a negative charge, and cation means it has a positive charge. But if you take away an electron, we're going to get to this by the end of today. When you take away an electron, then it loses a negative charge, which gives it a positive charge overall. And sometimes when you have like a lone electron, it's really likely to be lost. Sometimes when elements just want 1 more, they're likely to gain electrons. And we'll talk about, so typically some elements, they typically either have a negative or a positive charge, but very few can do both. Okay, so, oh, did I get ahead of myself by one? I probably did. Okay. Okay, so. Okay, so we'll do this one first. Okay, so you're gonna be group one. This table is group one. This table is group two. Y'all are group three. You're group four, group five, group six, group seven, and group eight. Okay, so this table here has 10 rows. So you're gonna pick the row with your number and you're gonna fill in this table. And you've been given an example. So the example is chlorine 37, -1. So the atomic number of chlorine is 17. You can look that up on your periodic table. Because we're calling it chlorine 37, they're telling you that that is its mass. So its mass is 37. And whether you know that either you know that it has a charge or you know how many electrons it is, either way, there's a negative charge of -1, which means there's one more electron than protons. And we know there are 20 neutrons because 37 the mass minus 17 protons equals 20 neutrons. So because the mass, so just for the mass is always equal to the number of protons plus the number of electrons. And then your charge is going to be the number of protons minus the number of electrons. So if you have the same amount of protons and electrons, it's going to be 0. So here, this 0 tells us that there's an equal number of protons and electrons. This -1 tells us there's more electrons. And then whenever you get yours filled out, just check with it. Okay.
Oh, so we have to find out. So find out why would these be find out what are.
Yeah, so, yeah, you have to choose your row. So some people have an easier row than others, but that's okay. That's too high.
Why no atomic numbers?
Yeah, no God,
Unbelievable, bro. This is the number of protons.
Oh, I wrote it wrong. Oh, my goodness.
Yeah. Right here. Yes.
Sorry, neutrons, 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 neutrons. These think, okay, think isotopes.
You know that your protons
Isotopes and neutrons go together. Isotopes, mass, and neutrons, ions, charge, electrons.
Atomic number is just.
Atomic number is just the amount of protons. That's it.
Some carbon,
Eight. Okay, so our atomic number is yeah, so that's what you look on the screen. Which is the very thing. The atomic number pops up. Right, what you guys
I'm sure my president.
Yes, I really like your. Were you there this last summer? Always a part of it. Yeah, I see all the rest of the guys. Yeah, they got always.
So how do you find like?
Okay, what's the math? Yes.
Oh, gosh. Okay, I thought that was.
Hey,
Okay. Oh, wait, you see that? Yeah.
They're eight. So here we're going to the electrons. So electrons and electrons are equal. Yeah. This is gonna affect the.
Why is this one?
What you gonna do with all the electrons?
Yeah, so it's basically you're using the.
Guys, that's the format for isotope notation. That's where everything goes.
Yay, thank you.
That's handwriting.
You see this? That's the negative one, and it's there too. Yeah, that's what you're writing it down.
That's what we're talking about.
Good.
What the slides that we went over.
Hey, Ralph, you want to talk?
So.
The other one, you guys got one down, do more.
And it has one more, I added one from what that is.
Go check your word.
That's all you gotta write. And just write the changes in that. Electrons. And then protons change again.
Good. That's good?
Yes.
Yeah, you're missing some stuff, so you just gotta upload more stuff. There's images of there's a report and then there's images of your graph. I'll check. I clicked all the buttons. Oh, okay, let me go back and look. I can go back and look at the computer. Yeah, okay, cool. Then I'll regrade it. Okay. Awesome. Okay.
Okay, so has everybody done with their row at least?
Yes.
Okay, row one. What is the atomic symbol for your isotope? Mg, so we have Mg. And what was its mass? 36? 26, so I'll put the mass here. And what's its atomic number?
12.
12. Awesome. And does it have a charge or no? No charge. So you could put a 0 here or just nothing there. Cool. So magnesium 26. Awesome. Okay, what about number 2? What was number 2? Row number 2, what's the atomic symbol that y'all looked at?
Calcium.
Calcium. Awesome. So the shorthand for people, dude, you'll notice scientists like to make acronyms and shorthands for everything. So we've got calcium. What was its mass?
41.
41. So we'll write the 41 in the top left. What is its number of protons or its atomic number?
20.
20. And does it have a charge, yes or no?
Yeah, plus 2.
Plus 2, so you can write the charge here. So this is our way of communicating all the relevant information. With just this here, we know it has 20 protons, 21 neutrons, and how many electrons?
Electron
18, which is how we get this positive. So 20 minus 18 is plus 2. What was the third one? What's the atomic symbol for the number 3? C for carbon. Awesome. What was its atomic mass? 41.
Or sorry, 14.
14. Okay. 14. And how many protons does it have?
6.
How many neutrons does it have?
8.
Awesome. 14 minus 6 equals 8. And does it have a charge? No charge. Awesome. The fourth one. Row 4. What was your atomic symbol? TE.
Tellurium.
Tellurium. Awesome. And what is its atomic mass?
128.
128. How many protons does it have? Uh-oh.
52.
52. How many neutrons does it have?
6.
76. Cool. 128 minus 52 equals 76. And does it have a charge, yes or no?
Yes.
Yes. What was its charge? Minus 2. So how many electrons, if its charge is minus 2, how many electrons does it have?
54.
54. Awesome. So 54 minus 2 is 52. So this is the mass. This is a reflection of number of protons and neutrons. This is the atomic number, which tells you it's how many protons it has. And this is the charge, which tells you how many electrons it has.
How do you find the electrons?
You find the electrons. The number of electrons is the charge. So you take the number of protons. So if you have the charge, then you know the charge is protons minus electrons. If you need to find the charge, it's number of protons minus number of electrons. Yes.
I was just gonna point out, so sometimes this is confusing. If you guys look at your periodic tables,
I know.
you'll see the atomic number is written in the top left corner. But when we do isotope notation, the atomic mass is in the top left corner. So I don't know why chemists decided to do that.
Yeah, it is a little.
Just to confuse you guys a little bit more, but that's just a weird difference. So when you look at your periodic tables, the number is in the top left corner, but when you do isotope notation, the mass is in the top left corner.
Yeah, they should have just written it like the periodic table and put in like the mass down here and the number
I
there.
guess the idea is you take the mass and you subtract the atomic number.
Yes.
You can find the number of neutrons really easily when you look at isotope notation. Right? So it allows you to do like a quick math problem to figure out how many neutrons are in that atom.
Yes.
I think that's the thinking there.
I think so too. Yeah. Okay. Okay, moving across the row. So row 5, what was our chemical atomics or the symbol of your element? Fe or F? Awesome. And what element is that?
Fluorine.
Fluorine. Awesome. What is its atomic number? How many protons does it have?
9.
9. And its mass? 19. So how many neutrons does it have?
10.
Awesome. 19 minus 9 is 10. And does it have a charge, yes or no? Yes, what was that?
-1.
-1. Awesome. So it has one more electron. Beautiful. So fluorine, -1. Number 6. What did y'all get for, what was your element? Oxygen. What's the symbol for oxygen? Oh, beautiful. What's its atomic number? 8. And what's its atomic mass? 18. So how many neutrons does this have? Beautiful. And does it have a charge? -2. Beautiful. So it has 2 more electrons than the base element. Okay. Number 7.
That's 10. Number 6 had 10 neutrons.
10 neutrons and 10 electrons. So 18 minus 8 is 10. The mass. So 18 is the mass minus the number of protons gives us the number of neutrons.
Why is it 10 electrons?
10 electrons because it has a charge of -2. So the way we get a charge of -2 is 8 protons minus 10 electrons gives us -2.
Oh.
Yeah. For this particular example. So if we look, so oxygen, so what we were given for this problem was 18 and -2. So this is what you were given. The problem was given 18 and -2 and oxygen. Because it's oxygen, we know that it has 8 protons. And then we do our math. So 8 proton, the mass is 18, the number of protons is 8. That means the number of neutrons has to be 10. 18 minus 8 equals 10. We're given a charge of -2. So the way we get -2 from 8 is we subtract 10 electrons. So these are the 3 equations that you can use to solve this whole table. Awesome. Okay, and okay, so just fun fact that we'll like get into that this has set us up nicely for. All of the elements in the second to last column often find themselves in a -1. Oh my goodness, yes, I almost brought Annie, I'll bring Annie up, right? Okay, so all of these tend to have 1 extra electron. That's something that they have in common. Everything in the oxygen column, they often tend to be in a -2 state. They like to take 2 more electrons. These guys like to have 3 more electrons. These like to have 4 more electrons. All of these over here, these tend to be in a plus state. They like to give away their electrons. They tend to be a +1 and a +2 and a +3. So these are not like, these weren't just made up for funsies. These are like real common life situations. Like you often find oxygen with a -2 charge. You often find fluorine with a -1. You often find calcium with a +2. Anything in the same column of calcium will oftentimes like to lose its electrons and become positive. And we'll get into that more throughout the lecture and in your textbook. Any questions about this table? And then you've just got 2 more to solve on your own before you're ready to submit it for your homework. Questions about the table? Wait, no, we missed 2 more. What was the 7th element?
Iron.
Iron, and what's its symbol? Fe. How many protons does it have? 6. What was its atomic mass? 26. What's its atomic mass? 56. So how many neutrons does it have? 30. Awesome. 56 minus 26 equals 30. And did it have a charge? Yes or no? +3. Awesome. And then the last but not least, 8, what was the element? Sulfur, it's just the S, correct? Yes. And what's its atomic number? 16, what was its atomic mass? 34. And how many neutrons does it have? 18. 18 plus 16 equals 34. And does it have a charge? No charge. Awesome. So it has the same number of protons and electrons, no charge. Okay, any questions about this table? Yes.
How would you find number of electrons if they have charge?
The way, if you find the number of electrons, if you have charge, so if it gave you a charge of +3 and it told you you had 5 protons, you're going to solve for this equation. So the number of electrons is +3 minus 5, so you'll have 2 electrons. 5 minus 2 equals 3. So the other thing to remember, so another shorthand for protons is P plus, and a shorthand for electrons is E minus. So protons have a positive charge, electrons have a negative charge. If you have more protons than electrons, it's going to be positively charged. If you have more electrons than protons, it's going to be negatively charged. Does that help? Okay. Any other questions about the table? Okay, let's do one more. This one is going to be simpler, but we started this on Friday. So let's go around the room. Everybody can pick one. So you were asked on Friday to pick an element that starts with the same letter as your first or last name. Yeah. And then from the periodic table, identify its mass, its atomic number, which is equal to the number of protons, and then subtract these two and tell me roughly how many neutrons it has. What's up? Yeah, let's wait like 2 minutes and then we'll go around the room. Yeah. 617. Okay, y'all have one? Okay, we'll listen to what everybody has and I'll write it up here in this notation. So what was your element that you chose? Chlorine, so Cl. What is atomic number? 17, and its atomic mass? 35. Awesome. So from this, you can subtract those two and get the number of neutrons. Beautiful. What was your element? Rubidium, RO? RB. And what's its atomic mass? 85. And its atomic number? 37. What was yours? Barium, Be. How many protons? 56. And atomic mass? 37. Okay, back corner. What was your element?
It was,
Fluorine? FL? No, it's F. And what's its atomic mass?
oh, sorry. You're talking about, my name.
Yeah, with your name. Statium. Is it RS or RT?
Yes.
DS? Oh yeah, fun. Okay. What's its atomic number? Number of protons? 110. And its atomic mass? 281. So you can tell by looking that this guy has a lot more neutrons than it does protons. Beautiful. Yours? Oh, did I not write big enough? Okay. I saw a squint. I'm like, I could write larger.
Sorry, I did krypton.
Krypton, KR?
Yeah.
And its atomic number?
36.
32. And atomic mass?
36. Atomic number 36.
Atomic number 36 and its atomic mass?
83.
83. Next. Einstein. EI, what is it?
Yes.
ES. Atomic mass? 152? 252, wow. Okay, I wrote it in the wrong spot. 252 is the mass. And the number of protons? 99. So again, like what we were saying earlier, this is our atomic, the atomic mass is on top, the atomic number is on the bottom. If we subtract these two, this is the number of neutrons. So we can tell a lot of these elements have a lot of extra neutrons lying around, especially those like transition metals we'll talk about later. They have like a ton of extra neutrons, which is why their mass is not just double the atomic number. Okay, we'll go, yes, okay, sorry.
Mercury.
Mercury, what's its symbol?
HG.
Hg. And atomic number?
80.
80, atomic mass?
201.
201, whoa, it has a ton of extra neutrons. Okay, we'll go across to the left, right next to, I forget your name, next to Kyle. Brody, which one did you pick?
Manganese,
Manganese, Mn?
and then, yeah,
Atomic number?
25,
25, atomic mass?
54.
54, awesome. It has 4 more neutrons than it does protons. Sometimes the math is easy. Your element? Which one, cadmium? What's its symbol? Db, awesome. Atomic number? 105. And atomic mass? 217, awesome. Yes.
I chose lead.
Lead, Pb?
Yeah.
Awesome. These two are so close. Db, Pb. Okay, and its mass?
207.
207. And its atomic number?
82.
82. Ooh, gold. What's its symbol? AU. And atomic number? 79. And the mass? 196. Awesome. Okay. Do you want to hear all the rest of them, or do you understand the idea how we change the protons? You change the element, change the neutrons, you change the mass, change the electrons, you change the charge. Cool, so everything on the periodic table, everything is uncharged. Out in nature, it might get a charge. Cool. Any questions about this? Yay, okay.
Oh, this.
Yes.
With the, what was the bearing of the particle? I know we've been over that on site.
Okay, yeah, so. For. Okay. So I showed you a link to a blog post earlier, but if we go back to these slides, so the atomic number is the number of protons. So the number of protons is characteristic of an element. So if you change the number of protons, what are you going to do? You're going to change the element. Yeah, so see how every single one of these elements up here has a different bottom number. The bottom number is the number of protons. If I could somehow add a proton to oxygen, it would become fluorine. Fluorine. So if you can add a proton, you're going to dramatically change every single property of that element. It's going to become a new element. Protons. Protons are like, I like this, the fundamental characteristic that all atoms of the same element share is the number of protons. That is the only thing that's saying. There's like a million oxygen molecules out there. Some of them have more or less neutrons. Some of them have more or less electrons. They all have 8 protons. So if you change the number of protons, you change the element. Okay. Yes. Okay. Isotopes. Isotopes are elements that have different number of neutrons. Okay, so let me write a different color here. Okay, so the atomic mass of an element is equal to the number of protons plus the number of neutrons. So if you change the number of neutrons, you change the mass. And elements that have different numbers of neutrons are called isotopes. So there's 2 answers for that one. You change the number of neutrons, you change the mass, and you create an isotope. Both of those are the same thing. Okay, and I don't have a slide about it, but where did you go? Because it's like the subject of chapter 3 is ions. So next week, we're gonna go into more detail, but if you add or remove an electron, you create a charge. So the charge is equal to the number of protons plus the number of electrons, or it's really more like minus the number of electrons. So if we add more electrons, we're going to create a negative charge. If we take away electrons, we're going to create a positive charge. So adding or taking away electrons creates an ion or creates a charge. Cool. Does that make sense? Okay. We're gonna, like I said, all next week, we're gonna mess around with electrons and make ions and ionic solutions. But today we're gonna go into how that is possible. Okay, so cool. We've got beautiful. Okay. So we got like 20 minutes. We'll start kind of going. So sometimes they discovered things about the discoveries. They have had observations and they led to future discoveries. So one of the things that scientists used to do was measure the atomic radius, how big the atom was. They could do this by like scattering light and measuring how far apart the electrons were from the nucleus. And what they noticed, so this is like a schematic of the periodic table. This is also on Canvas already. I linked to it on the modules page. So what they noticed was these two elements right here, CS and FR, they had the biggest atomic radius. They have like the biggest atoms of all. You might think that the right side would have the biggest, because like there are more and more electrons and more protons going to the right. So you would sort of think like more electrons, more protons to the right, but no, these are the biggest. And so we'll kind of go over the next few chapters. The bigger the positive charge in the middle, it like pulls the electrons in. Yes. Okay. So so they started with an observation by measuring all the masses, and they noticed that the atomic radius is smaller as you move across. So how is that possible? This helps us understand the atomic theory and how electrons and atoms are shaped. So this, my x-axis is kind of cut off. But so this is a figure in your textbook showing the atomic radius and the distance. Okay, so the atomic radius is the distance from the nucleus to the outer electron shell. So there's multiple electron shells. We'll go over that. The outermost shell. On the bottom is our atomic number. So we can see we have hydrogen, helium, lithium, barium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium. So it starts off with like the one on every element on the far left column is fairly big in size. And then the next element to it gets a little bit smaller. And it's bigger, smaller, bigger, smaller, bigger, smaller. And so this, as you go across the rows, the left one is going to have the biggest radius. Everything to the right is going to be pulled in closer. And so these are color-coded by information. These periodic tables are grouped into blocks that have to do with their electron shells. And we'll go into that just a little bit more on the next couple slides. But does everyone understand how to read this? So we have atomic number, sorry it's cut off, and the radius on the left. So you can see these trends of how every element on the left, this is a periodic table, atomic number 1, atomic number 2, atomic number 3, 4, and you can see how their size varies with atomic number. That make sense? And so what they were able to do is they started grouping these periodic table elements into blocks according to their outer electron shells. And so this first one here, the first row, this is the row with hydrogen, lithium, sodium, potassium. These all are in the S block. And there's the first S shell, the second S shell, the third S shell, the fourth S shell, the fifth. So there's one S, it goes like this. One S is closest to the nucleus, 2S is a little farther out, 3S, 4S, 5S. And then it jumps all the way over here to this P block. And so we have 2P, 3P, 4P, 5P, 6P. And then our transition metals have a D block. So there are 2 electrons in the S block, 6 electrons, 1, 2, 3, 4, 5, 6 in the P block. There's 6 blocks there's 6 orbitals in each one. Okay. And this is how many electrons are able to fill each of those. So there's 1 electron in the outer shell of hydrogen, 2 electrons in the outer shell of helium, 1 electron in the outer shell of lithium, 2 electrons in the outer shell of barium, 1 p orbital in boron, 2 electrons in the p orbital of carbon and nitrogen. And so this is how, so these blocks map onto this S, D, and P blocks map on to this earlier. They aren't color coded exactly the same, but when you add a new S shell, the radius increases. As you add more electrons, though, they get pulled closer and closer because the nucleus is very charged. I'm going to move this over just a little bit. Okay, so if we're looking at this electron table, these are the different orbitals that correspond to the blocks. So the s orbital corresponds to this s block here, and 2 electrons can orbit that shell. The p orbitals correspond to this block of 6 elements here. They can have 6 electrons. And there are 5 d orbitals that can handle the 10 electrons in this transition block. And then there are 7 f orbitals that can occupy these 14 electrons. So the table matches these electron shells. So we can do some pretty complicated writing out of where the electrons are occupied, but just know that they map on perfectly. This is the S shell, it can have 2 electrons. This is the P shell, it can have 6, D, 10, and F, 14. Okay. And so the way people write out this is one way that people started writing out how many electrons were in each orbital or each shell. So hydrogen has 1 electron, helium has 2 electrons. And basically the reason why we can get charges, the reason why we get positive and negative charges is because elements prefer to have their shells filled with electrons. So oxygen, this is an example of oxygen. Oxygen has 1, 2, 3, 4, 5, 6, 7, 8 electrons. The reason why we often find oxygen in a state of -2 is because it likes to steal electrons from other elements to fill its orbital shells to be balanced. Nitrogen has 1, 2, 3, it has 2 electrons in the 1s shell, 2 electrons in the 2s shell, 1, 2, 3 electrons in the p shell. The reason why we often find nitrogen can either give away 3 electrons or take 3 electrons to fill those orbitals. This is going to be the subject of chapter 3 and 4 in more detail. But this is how we write out these orbitals. Okay, but I think this one here is more useful. So we'll start with a couple. So Bohr, the very first slide that I showed y'all earlier, he knew that he hypothesized that the electrons orbited in rings. And so helium, this is its 1s orbital. It has 1 electron in that 1s orbital. Helium has 2 electrons. It has 2 in this orbital. Lithium has 2 in the first and 1 in the second. Barium has 2 in the first and 2 in the second. So these are how its 4 electrons orbit the nucleus. And then aluminum, if you can find it on the periodic table, it's in the third row, the third column. Because it's in the third row, it has 3 rings. And it's in the third column, there's 3 electrons in its outermost ring. So this outermost ring is called the valence shell. And we're gonna work on, we'll go over more problems on Friday that talk about putting this into action. I don't have them today because we're not quite ready yet for them, but I'll go ahead and we're gonna get into these. This is the last thing that we'll go over is another way to visualize electrons, but we'll cover this on Friday. And we'll cover the properties. Oh, that I probably should have gone to. So after you're gonna do a lab on Friday experimenting with metals. So on Friday, when we come to class, we'll talk more about metal properties and how those properties of solids and liquids and gases fit onto the table. Okay, any questions for now? You are gonna get to draw these on Friday. So this is a primer. We'll put it into action on Friday. Cool, any questions so far?
Oh,